If it has attained in the third number of pass itself, my simulation will get stopped here. If it has not stopped till the 10th number of pass, I had not attained this 0.02, automatically my simulation will stop here.
That's the maximum number of
Maximum number of pass which we have given.
Okay.
So I would always recommend like minimize the convergence rate, like del S value, whatever you are giving, minimize it and maximize the number of passes.
But it
So
will take
simulation
too
will be
much
fast.
time also.
Too much of time.
Too much of time. It will be
But
taking.
the accuracy level which you get, it will be there. But what the thing is like convergence rate, if it is attaining before itself, the number of pass, for example, if you go 100 also, if you are getting in second number of pass itself, this 100 cycles won't happen. The first target is like convergence rate should be attained. Then it's not about the number of passes, how many, like if you give 1000 number of passes also, it doesn't matter. It's about only the
It
convergence
only
rate.
takes only few. Once it attempts, automatically it will
It depends upon the structure how you are making it. For example, if you go for fractal antenna design, there will be lots of small capacitive or inductive structures will be there. So in that particular case, we need to go for confined meshing there. For a patch antenna or simple antennas or any kind of where my structure is not much complicated, I can go with the normal model there.
No, if I decrease the del value, the time taken for simulation will be increased or decreased?
Increased.
So and also like this is like a meshing has a tetrahedral, hexahedral, those kind of meshing is there.
Tetrahedral meshing we use in that is in ANSYS we use tetrahedral meshing. The benefit of tetrahedral meshing is you can compactly corner this like edges or corners, it will be considered, or this particular square edges it will be easily considered here.
Okay.
But if it is an hexahedral structure, that's what we say like HFSS is more accurate than CST because they use hexahedral structures.
But they say, but they told like time domain is much better than FEM.
We have time domain also for that. Actually, they say all have merits and demerits, to be frank. But in accuracy level, based on the earlier stages, but I don't know how CST, that change in you can see.
Like we can change, we can give both the meshing in CST.
Yeah,
also.
now they had included, but the nominal one was hexahedral, but tetrahedral structures concentrates corners also. There won't be neglection of that corners, so always tetrahedral structures if we take, the accuracy will be more.
When we compare these two results in CST and the HFSS, I see the gain is increasing in CST.
It's again depending on the approximation or the tetrahedral structures.
So materials materials play a prominent role.
Actually, what I say is here they say as the permittivity of FR4 is 4.4.
Yeah.
In CST it will be 4.3.
3, yeah.
So that also plays a
That
role.
also, yeah.
The permittivity value which they are using.
And
Like-
they are using 99% pure copper, say in CST. Here they are using 97% pure or 95% or something like that.
Basically, the material properties, whatever we give, that also plays a role there.
And also the solver type. We are using time domain solver in CST, no? Here FEM solver.
Finite frequency, it is mostly of frequency plays a role. Both has merits and
To use
demerits.
it like we should do it in CST itself with the time domain solver and the frequency domain solver. Within CST itself, you will find some difference.
That is
That updated version is also changing the things. I see the results.
These slides can be given, sir.
Yeah, this will be given. So this is the overall process how we go for, and last one is post processing here. So as a scratch of this particular simple model or a rectangle patch antenna will make at microwave frequency range or millimeter wave range at around 27 to 28 gigahertz. We will just design a patch antenna so that you will get to know the model. If anyone wants to do hands on, they can start now. Just we'll go as an in a flow.
You can go with the patch antenna.
So the first thing is initially after opening electronic desktop, you can go to project, then click on insert HFSS design. So these are the different types of layouts you had got as per this particular flow. I had chosen the design here. So the first thing is design has been chosen, the next step is solution type. So for choosing solution type, you can go to HFSS, go for solution type here. Once you go for solution type, this HFSS means the FEM, only the FEM solver which I am going to use. Then HFSS with hybrid and array means the combination of three solvers
Integral
together.
solvers and
FEM, then HFSS IE, then array, that is my DDM solver. These three solvers will be combined here. Then this is the time domain solver which we have in here, the transient solver. Then SBR plus for radar simulations. Then eigen mode and characteristic mode for ResNet mode analysis. Okay, so these are the different solvers which we have. So always I would recommend to go with HFSS with hybrid and array, so that if you are continuing once you have designed your antenna, if you are going for array, automatically it will take it. You need not to shift the solver and all here.
MIMO also
still we are
can
getting the accuracy of HFSS, right?
Yeah.
Sir, we can
Still
use
it will
MIMO
be-
also in this option.
Yeah.
Okay.
So once we had selected solution type,
The network analysis.
So that go 1 second, sir. Like there we have model, terminal, and all.
model, if you want to analyze the modes in your excitation.
Solution.
Here, if you want to go for model, you can go for the modes, excitation modes if you want to go for. In terminal, we don't have excitation modes. It will take the prominent mode, whatever it has been inbuilt. Like we'll be having a resonant ground plane, it will be the terminal, and whatever the transmission line or the model which we are using. Okay, basically, let's suppose if you are analyzing any kind of different types of modes you are exciting and seeing for each and every mode of excitation, how my results are varying. So in that particular case, you can go for model. For
In filters we can do.
yeah, you can go for model.
Like based on the modes, like excitation, we can change the design. Like we can customize the electromagnetic our frequency.
Frequencies and all. We can customize it. That's what at that particular frequency, which is the for that particular structure, which is the predominant mode.
Yeah, predominant mode.
mode
That we
which
can
is-
at that point we can
we
change
can
some
change.
design changes. Now then we can
That we can go with model.
model.
So in this case, we just start with terminal to understand how we assign excitation. If we go for model, then we have to showcase how my excitation or the field lines should go on.
Okay.
That will make bit complicated. Just we'll start with terminal and then we'll shift to model also. So once you had inserted or you had chosen the solution type, the next thing is we have to create geometries here. Okay. So for creating geometries, the first thing is we need to draw the structures. Basically, I will go for an probe feed patch antenna. So the first thing is we need to draw a substrate here. Okay, for substrate, it is a kind of a rectangular box kind of a structure which we need to make it. So go for draw box option. Either you can give the values here. This is nothing but the coordinate system, the initial position of that particular geometry. Either you can give it out here or just randomly you can draw a box and you can edit it over here. Okay. So for example, in this case, 6 mm is the substrate size here. So I'll go for 0, 0, 0, which is nothing but the starting position. I'll keep it as origin for the box here. So the X size is 6 mm, which is my.
We need to define the like dimension there, 6 mm.
Actually, we have to define. I was using this particular model. We can just change the unit here. If we go to modular units here, we can change the unit.
We can set, and once it's set, it's done, right?
Yeah, it will be the default unit.
Okay. Now we need not to give
Need not to
mm and
give
all.
any kind of millimeter. That is not needed. The default unit will be millimeters here. So 0, 0, 0, the substrate size is 6 mm. Then that is 6 mm along length and width, which is along x and y axis. I am taking it as length and width, and along z axis it is height, which is 0.254 mm. So this we had created as a substrate. Apply and OK. Just to fit into the screen, use Ctrl D as a shortcut.
Okay.
So it will be fitting into the screen. So this is the box or the substrate which we had made. Okay. So once we had made this particular substrate, then the next step is we need to, in a patch antenna, it will be a kind of substrate. Bottom will be ground, top will be the patch. and then we'll be creating inner conductor and other dielectric regions for my probe fit technique. Okay, so the first thing is we had created the substrate, then we have to assign material property to it. So in this case, go to box 1, right click, go to assign materials here. Just once you click on assign materials, it will ask directly material library will be opening here. You can go for materials, which for this particular antenna we had the dimensions I had used Rogers material I had used
Stop,
here.
okay? Nothing, you just keep on.
It's not working in the lab.
You type
Yeah, this is the material. Rogers RTD, right? 5080 with a permittivity value of 2.2 and loss tangent it will be around 0.0009 I think. Okay, so once I click OK, now my material from vacuum it will be changed into Rogers RTD, right? Okay, so once this is done, the next step is I need to create an ground plane. Okay, for ground plane I am just taking a lossless case where infinitely thin sheet I will be taking here. So for that I will go with rectangle. So draw, then a rectangle. Here just you can just randomly initially draw it and then you can give the numbers here. Or else if you want to give variables,
we can select the face and give it. We can select the
yeah,
face.
that also could be done. Or else you can just draw a rectangle. That also would be done. So then you can go for this particular rectangle creation, and this particular rectangle represents a copper material. Okay, which as we don't have thickness, only for 3D material we can assign material here. For assigning the material property of a copper, we have boundary conditions here, which is perfect E or finite conductivity. You can use any of this. So I'll just go with perfect E here and click OK here.
Sir, PEC and perfect E difference, sir. What is it?
Nothing. It is, if you are going for 3D structure, it will be PEC. The material property will be like both copper, it will be almost matching with copper.
Copper, VEC, PE,
Everything will be like, it's nothing but perfect electric conductor. Okay. 2D, the same perfect E will be going. So now we had created an ground plane here. Then the next thing is we need to create patch on top of the substrate. So you can go for draw again. Go for rectangle, just initially randomly draw it. Then we should know where it should be. The overall size of my particular patch is 3.34 and the size of this particular substrate is 6 mm.
So it doesn't have an inbuilt calculator and all, like CST has.
No, don't have any.
So we
In
cannot
HFSS 3D layout it is there.
We
So-
cannot calculate microstrip planes and all.
No, in HFSS 3D modular we do.
Yeah, any software is not there, we have to define.
CST is there.
No, we have to
we have
define the-
macros.
That's
macro,
just for
if you
the
see
port we
construct-
can decide it there. Calculator is the port.
Microstrip also there. You can calculate the microstrip width line, port, everything you can
So
calculate.
6 is my
For
substrate
some, certain
overall
shape.
length,
Okay.
and my
Using
patch
macro
length is
option is there, no?
3.34.
In
So
macro,
the gap
you will have a
between
calculate option.
my patch,
In the
that is
calculate
from my
option,
edge of the
you
substrate
select
to
it,
edge of the
then
patch.
you will have all
That
the calculators.
on both sides
CST.
it is 2.66. So half of it
You
will
can
be
calculate
1.3.
everything
How
with
did you
the
take 3.34, sir?
No need for it.
That,
like,
I had the
those
calculator.
MATLAB codes are like pre-integrated in
Using
CST.
formulas I had calculated it.
Okay.
Definitely.
So we need not go for
You
MATLAB
can
and
see
all.
here, this is
You have
using these
CST.
formulas I had calculated this. And these are the dimensions, and this is using from Balani sir's book only I took this formula.
There are some
So it is 2.66 on both sides. Now it is around 1.33, which is the starting position of this particular geometry. 1.33 comma 1.33 along y also, and along z it will be on top of the substrate, so it is 0.254.
254.
And along x it is the length of the patch, which is 3.34, and again along with it will be 3.34. Then we can click on apply and OK. Now you can see the patch has been created. So again we are going to assign boundary, which is perfect E to this, and we can click on OK here. So now we had created a substrate, then the ground plane and my patch here. Once we had created this, the next thing is we need to create the coaxial feed. For coaxial feed, the first thing is we'll create inner pin. So for that, we'll go for cylinder option.
This is quite difficult, sir. Like,
So we first check the surface current there.
Sir?
We first check the surface current there.
Yeah.
Then only we can decide it. No, that's where the highest surface current. Then we.
Yeah,
decide
that
the
we
force.
can go, but
we have formulas to
actually
like
we
feed.
have formulas
No,
where
for this
For
one.
feed also we have formula, like this pin also we have a formula.
other than that I would say you simply like if you need to find it, the simple way is in center of patch the impedance will be 0.
Okay.
At the edge of the patch it will be maximum.
Okay.
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 Run an optimetrics, run a parametric sweep, like your feeding pin will be changing from 0 to the maximum edge with a step size of 0.2. At some point you will get to know like what is the reflection coefficient. Based on that you can say this is the maximum impedance where it is matching.
But it takes so much time. Better than we can check the surface current there. Surface distance.
Anyhow you need to feed it, na sir. Then only you can
How
go
you
for
can give
surface
the
current.
like feed?
After-
Which feed you are going for to give?
Before feeding, how do you check it?
No, surface
No,
current
in
is
in a CST it's must have to set the
Excitation
split
here
line.
also it's must. You
It
have
is-
to give the
no,
excitation,
sir.
then only.
The
No,
simple
I
log-
see a
simple thing is
somewhere.
like once you give the source only, then only the structure surface current will be displayed. Like whenever you are passing some signal from this end to this end.
Okay.
Okay.
One FDB I see this same thing they are showing that first they are checking the surface current and then they added the port there.
No. First they will add the port and they will check the surface.
Yeah.
Then again they will check.
Okay.
Okay, first at some point they will excite it. Okay,
Mhm.
so
Maybe
based on
at
that,
excited
they will
at
see,
some points, then they will
then
check
they will
accordingly.
see wherever the surface current is maximum, then they will try to point it out.
Okay.
Okay,
Or
without kind of exciting a structure, we can't see how the surface current is getting distributed.
or we can go for parametric analysis, optimetric analysis.
So once you create this particular cylinder, okay, the dimension you can say initially I can keep it as 3, 3, 0 at center. Just I'll show you that optimetrics also how to run that. Okay, so at center I'm keeping as of now whatever I'm sending from this coaxial cable, it will be fully reflected back.
But the
Because-
reference plane is in 0,0,0 only.
Yes, sir.
Center plane.
Yeah.
Then we are-
No, edge of that particular
Yes,
plane.
one of age we
the
have to go now.
thing is like,
So now you are keeping it in edge.
so the starting position is this one. This is 0,
Okay,
0,
okay.
0.
It's a
Okay.
The height of the substrate will be
That's
there.
Here it is like only
This is
the-
between CST and
and,
HFSS.
yeah.
The difference between CST.
It will take like the symmetric structure.
Yeah.
Like
Okay.
whatever the first structure you are making, it will take the center point will be the point of that particular structure, and it will take as symmetric. Here instead of that, you can create when you want to create that.
Yeah, we can change that
coordinates based on your wish. You can change that coordinate here.
You
So
can make
here,
it up to the patch center also. You can select the face and.
so what you can do here is you can just double click on this. Here I'll keep it at 3, 3, 0. Then my radius will be 0.1 in this case, and the height of that particular
मैं 5
inner
मिनट बाद
cylindrical
तुमको
structure
दूंगा।
will be 0.254. And click on apply, and okay. Now it is at exactly at the center of the substrate and
ये लाइट पड़ रही
the
है मेरे
structure
पर
here.
मैं क्या कर रहा
Then you
हूँ
can assign material property to it. Right click, go to assign material,
So perfect.
perfect or copper. Anything you can go for.
मैं जैसे कर रहा हूँ ये लाइट
So,
बिल्कुल सेंटर पे
copper ஆஃப் பண்ணிக்கிறது ஒரு வாரம் ஆயிடுச்சு, அதனால திரும்ப ஷட் டவுன் பண்ணி ஆன் பண்ணி ஹீட்டப் போயிட்டு இருக்கு. So cylinder we had chosen, like we had assigned copper as a material property to that particular inner cylinder. Now the next step is we have to create an dielectric region, or we have to etch out the metallic part from that ground plane here. Okay.
Yeah.
So for that I will be creating a circle. As it is a planar structure, that is it is a sheet kind of a structure, I am using circle. If I had used some thickness, I will be using cylindrical structure of that dimension, which it will be cutting it out. So the same way Just
First we had to take a circle and we can cut it and we can place the thing also.
yeah, anything is fine. Okay. Either you can create this particular structure first, that is circle first, and then also you can make it. Yeah, the only difference is the position will be same, only the radius will be changing here of that particular outer cylinder. That is this is nothing but
That
the
is
ground plane, ground
yeah.
of the coaxial cable.
That's only.
Okay, 0.2. So now this particular I am going to subtract these two here from rectangle 1, which is my ground plane.
Okay.
I am going to subtract this particular part. For that, once you have chosen, go to modular, boolean,
Boolean
then
subtract.
Blank part should be the part which has to be remained, and the tool part should be the part which has to be removed out. Then click on OK. That particular part circle has been, the area
Cut.
has been removed, and that is the metal has been etched out.
Okay.
So till now we had made all these conditions. There are two conditions. Usually I don't follow that part and trainings actually. What basically we will do is like we will in an coaxial cable excitation. So if this is the inner conductor,
Yeah.
okay, in here the ground will be connected to this particular outer conductor.
Okay.
So this will be the outer conductor, and this is the dielectric region, and this is the inner conductor, which will be extended again, and it will be touching my patch here.
Yeah.
Okay, this is how it will be. So what I will be doing here is either if you extend this line, you will be assigning a geometry of a circle, and
Okay.
you will be assigning the material property here, like excitation from here. Instead of that, instead of giving this here, I will be giving the excitation here itself.
Like at the ground itself, like
At the ground, the outer part of the ground will be touching. That is the outer.
Outer, like,
I will be creating a circle again
Mhm.
for excitation geometry. My outer circle will be
Touching the ground,
like
cutted part.
the edge of that particular ground, and the edge of the circle excitation geometry. It will be exactly touching, and the inner conductor it will be touching my patch there. So I will be neglecting this whole part, whatever we are making as an extra. Like you need not to go for in CST also you can check it out. The results are similar only. We have cross verified it. So what either if you are not satisfied you can extend that. It's just building a geometry again.
What about the dielectric part? Like we can use some polyamide or.
Actually it doesn't have any kind of thickness here. Okay. So if you don't have any thickness, directly it is whatever the source you are giving, it is directly. If you are using any kind of thickness, you can fill in this particular region. Let's suppose some kind of thickness it has. Okay. In this case, this also should be extended. This inner conductor also should be extended. In this case, in practical cases, it will be Teflon.
Sir, why not we cut for the that softed part also? The
Which one?
softed means cylindrically we cut the softed and then we add the feed there.
Which I didn't get.
Sir, the
It's
thing.
cutted already, like inner we cut like that.